Okay, so remember, this is Lagrangian, right? We're following material particles. So as this body is undergoing its rigid motion, it's undergoing a translation and rotation, we're fixing our attention upon this point, right? Parameterized by its reference position, capital X. We're now watching that point as it deforms, right? As the body, not as it deforms, as the body undergoes its rigid motion. Okay. Likewise for the acceleration, right? We're defining the acceleration. We're looking at this point and saying, okay, what is its acceleration? And we have those two relations for V and A. Now, if you think about it, this type of description of motion, where we are following the reference position of the particle, or thereby following the particle itself, is natural for solid mechanics. Okay? When we look at bodies deforming, we look at solid bodies moving past us, we tend to focus our attention upon specific material points, even if we don't really realize it when we're doing this. Okay? So this is natural. Okay, so let me just make this remark here. Remark. The Lagrangian description of motion is natural for solid mechanics. Okay? Let's demonstrate this by considering what happens with 2 points in this reference configuration. Okay, so we have the reference configuration, we have our basis, we're going to talk about rigid motion of this body. Let's see what it does for 2 points that we pick arbitrarily. Okay, so let's suppose the 2 points are here. Let's call this one x1, that's another point that we're going to call x2. Undergoes the rigid motion, right? So what's happening to those 2 points? How would one characterize the relation between the positions of those 2 points through the rigid motion, right? Well, the motion is rigid, so those 2 points have to remain the same distance apart at every instant of motion, right? And let's just check that that does indeed happen with rigid motion. Okay, so we have this basis. We have the body in its reference configuration, and we're going to talk about 2 points which I will denote x sup 1 and let's suppose x sup 2. Okay, we have the rigid motion, which is c of time plus q of time x. The body comes to a configuration that's related rigidly to the reference configuration. We have omega sub t. Let me draw the 2 points here. I think x1 would have gone here, denoted little x1, and x2 would have gone somewhere there. Okay? And what I'm trying to do here is also draw them the same distance apart. Okay, we want to check that those 2 distances are the same. This is easy enough to do because we know that x1 is phi of capital X1 at the time of interest, and x2 is phi capital X2 at the time of interest. Okay? But then little x1 is c of t plus q t x1, and x2 is c of time plus q t x2. Okay, if you're looking at the distance between points, we know how to write that out. We want to check what happens with this quantity, right? Which, of course, when we look at the two equations in the line above, is just qt x 2 minus x 1. Okay, and I realized I turned those from superscripts to subscripts here, so let me correct that. Okay, so x2 minus x1 is equal to the square root, right, from the definition of the magnitude of the length of a vector. It is just the square root of qt x2 minus x1, all of this dotted with qt x2 minus x1, right, and let me extend that square root symbol all the way. Okay, we have this. Now, something you know, and we can see this again if we go into coordinate notation, we know that we can write that dot product also as follows, right? We can write that dot product as using linear algebra notation, right? Using linear algebra notation, that dot product is, I'm going to dispense with the time dependence here, okay, just to save some writing. This is using linear algebra notation now for the dot product of two vectors, right? We can write that as, we can write the first vector as transpose, right? The second vector. Okay, so using linear algebra notation, this is how we write out the dot product. Okay, again, doing this with painful detail, what we get here is x2 minus x1 transpose q transpose q x2 minus x1. Okay. For q transpose q, we know that we have the second order isotropic tensor, right, because q is orthogonal. Okay, so this thing that just reduces to now square root of x2 minus x1 transpose x2 minus x1. All right, but this, of course, we know is just magnitude of x2 minus x1. Okay, so what we have then is that the magnitude of the vector separating the 2 points in the current configuration is equal to the magnitude of the vector separating the 2 points in the reference configuration. Okay, so this definitely satisfies our intuitive idea of a rigid motion. Okay, all right. So doing the sort of Lagrangian description of mechanics is natural for solids, right? So when we talk about this, think about this as a solid body undergoing a rigid motion. 2 points on it maintain the same distance apart. All right. Let's look next at what we mean by the Eulerian description of motion. Okay, so now this is going to be a little different. Again, we want to talk about the motion of the body just as we would by using Lagrangian descriptions of motion, but the way we look at the body is going to be a little different. Okay, we're no longer going to follow a particular material point. Instead, we're going to do this. We're going to say, okay, we have our basis. Now we're going to say, well, we are fixing our gaze at a particular point in space, right? Maybe that point in space, right? We're just looking at that point in space, right? We still have the basis, right? So we still have our same way of describing vectors. But looking at that point in space, we're going to stare at that point and then watch as our body comes tumbling past, right, or maybe deforming past. But we're still looking at this point in space. We're not yet looking at this body. We're looking at that point in space, and then as the body passes in front of that point, we record whatever we need to at that point in space. Okay? We watch the body go through. So yes, we do see the material particles go through, but we don't follow those material particles, right? We're looking at this point in space and looking at what happens as the body tumbles past. Okay? A more intuitive way of thinking about this is using this prop. Right? We have our fluid in this bottle, right? And I've taken the trouble to draw a black window, right? I hope you can see it. There is a black window here, okay? I've done this because, as you may imagine, the Eulerian description of motion is natural for fluids. So I'm going to shake this bottle. You're seeing the water in it, you know, sort of going past that black window. But now imagine that all you're looking at is that black window, right? And water is going past it. This is the natural way in which we look at fluid motion. When we see rain falling outside of a window, we're looking out that window. Our position in space is defined by that window, right? We watch the droplets of water, we watch the drops of rain falling past that window. We see the material moving, but still we parameterize it by the position of that window, not so much as following the particles as they go through, as they tumble from the clouds all the way down to the ground. Okay? That's an important distinction. Okay, so let me write this down. The Eulerian description of motion is to parameterize motion, but that also means velocity and acceleration. By position of a point fixed in space. Okay, and this is important. It's a point fixed in space, and it is not a material point. Okay? Consequently, we have our Eulerian or spatial velocity, okay, which we will denote as little v, okay, now parameterized by little x, the spatial position and time. Importantly, this Eulerian velocity is the same as our Lagrangian velocity. The vector is the same. It is just a matter of how we are describing it. So, whether we follow a particle on the body or we look at a point in space, I'm looking at this point and watching as the particle, that same particle tumbles past that point in space. Okay, regardless of how I describe velocity, the velocity is the same. It's just a matter of how I'm parameterizing that velocity. Okay, how I'm parameterizing that vector function of the velocity. Okay, so when I say this, when I say that little v is the Eulerian velocity, its definition still remains the same. Okay, and it is indeed equal to the Lagrangian velocity. Okay? Likewise, with the Eulerian or spatial acceleration. Okay? We're going to denote it as little a of little x and time. It is equal to the Lagrangian acceleration. Okay? let me write here Eulerian, and here Lagrangian. Okay? We're going to break for this segment here, but when we come back, we are going to look at how we write out this Eulerian velocity and acceleration explicitly for the example of rigid motion.